In this video, we will be looking at the concept of work and the work-energy theorem. In my earlier videos, I stated that the work done is equal to the change in energy of the system. Mathematically, we write W for work equals delta E for change in energy. Work represents the energy that is either transferred into the system or out of the system. So whenever the total energy of this system changes, then we know that we have work being done. The energy of the system could increase or it could decrease. It occurs because there's an interaction between something on the outside, some object in the surroundings, that is exerting a force on something in the inside in the system and causing the energy of the system to either increase or decrease. If you look back in page 2 of your notes, where we discussed Buffy and Biff, where Buffy was throwing a water balloon at Biff, we used a energy bar graph to help describe the storage of energy both initially and finally, and then we also defined the system to help discuss whether work was being done on the system or work was being done on the surroundings. So whether energy was increasing or decreasing in the system. So in this particular case, Buffy is the object on the outside that is exerting a force on the balloon and causing energy to go into the system. So it's really Buffy who is doing work on the balloon, and hence we draw this arrow going into the system to represent the flow of energy into the system. And this is called work. Depending on how you define your system, you could have the energy of the system to increase. So if you were to look at just the system being this shot put, then the athlete is exerting a force on the shot put. It's increasing in its speed, hence kinetic energy, and so the energy of the shot put is increasing because work is being done on the ball. However, you look at the matchstick. In this particular case, the chemical energy is being turned into thermal energy that is eventually leaving the system of the matchstick and going out into the surroundings, and hence the total energy of the matchstick is actually decreasing. Work is basically done whenever the energy of the system is increasing or decreasing. If you happen to define a system that is isolated, or sometimes called closed, then in this particular case, the energy cannot flow between the system and the surroundings. So all of the energy that's within the system, the total amount, remain constant. There might be some transformations between kinetic to chemical and chemical to gravitational and so forth, but the total amount of energy within the system remains constant. So in this particular case, since the energy initially must be equal to the energy finally, then the change in energy, which is the final energy minus the initial energy, must be equal to 0. And as we mentioned earlier, the work done equals the change in energy, and if the change in energy is 0, then the total amount of work being done on the system is also 0. So a system that is isolated or closed, the total amount of energy within the system remains constant. So the initial energy and the final energy are equal to each other, and in that particular case, there is no work being done by external forces. If you happen to have a system where it is open, where you can have interaction between objects from the outside of the system to objects that are in the inside of the system, then you have work being done. And if you notice, I've been talking about how about work involves a force. So hopefully, you might be thinking, there must be a way that we can calculate the work besides finding the change in energy of a system. And yes, there is. Work involves a force and a displacement. Let's consider the following example. Let's say you have a windsurfer in which the wind, which is on the outside surroundings, is applying a force on the sail of the windsurfer's board, or the sail of it. This force of the wind is doing work on the system, and hence the windsurfer is going from rest to some speed, and hence it's gaining kinetic energy, and hence the energy of the windsurfer system is increasing. There's a force being exerted on the system, an external force from the air, from the wind, and it's causing the system to move at displacement, which is represented by this d. In this particular case, the force is to the right and the displacement is also to the right. So the calculation for the work is actually rather simple. In this particular case, the work, W, is equal to the force multiplied by the distance, d. But be careful with this definition that I've just written down. Many students sometimes get mistaken in thinking that work is just simply force times distance. Well, this happens to be true for this particular case because the force is in the same direction as the displacement. So in this case, yes, you can just simply multiply the force times the distance. By the way, what do you think the units of work are in? Well, force is measured in newtons, and displacement is measured in meters. So the units of work are in Newton meters. But you also know that work is equal to the change in energy. And energy is measured in joules. So really, a Newton times a meter is really equal to a joule. And if you wanted to go even further, you recall a Newton, which is force, which is equal to mass times acceleration, and mass is measured in kilograms, and acceleration is equal to meters per second squared. So you could then further add this into here, and you would get kilograms times meters per second squared times meter. So a joule is really equivalent to a kilogram times a meter squared all over a second squared in our basic measurement units of kilograms, meters, and seconds. As I just pointed out, this formula is only going to be true if the force is exactly in the same direction as the displacement d. So how do you calculate the work done if, let's say, the wind was blowing at an angle? For example, consider this go-kart that is being pulled by this parachute with a tension in the string, represented with this force F, that is at some angle to the horizontal. It's not shown in here, but the displacement is to the right. So how does one calculate the amount of work done in this particular scenario? Because you can't simply multiply the force times the distance and get the right answer here. You see, not all of this force is actually making it move to the right. The only thing that's actually making it move to the right is the component of that force that is in the direction of the displacement. So actually the more correct way of writing the work done is work equals force and the parallel symbol times distance. That's the more correct answer here. But F parallel is not equal to F. So I just redrew this force over here to the right. We want the component of this force that is parallel to the direction of the displacement. First, let's choose an appropriate coordinate system. This is my y-axis, and this is my x-axis. And we really want the component of this force that's making it move to the right. So we want the horizontal component here. There it is there. And I'll just label this as F parallel. And we also have to have an angle. You'll notice there's an angle in our formula actually. Well, actually I haven't shown you the formula. Let me derive it for you. There must be some angle in here. Let's define the angle that is made with respect to the force vector and the displacement vector to be theta. And what trig ratio would you use that would involve the hypotenuse of this triangle, which is F? Usually that's what's given in the problem. And theta, which is also usually given to you in the problem. Well, that would be cosine theta. Cosine theta would be the adjacent side, F parallel, divided by the hypotenuse, which is F. So F parallel is really equal to F times cosine theta. If we now replace this with this, we'll get the work is equal to F times cosine theta times the distance d. And this is usually written as F times d times cosine theta. And work, by the way, is also equal to the change in energy of the system. So this, W, is equal to the change in energy. So when you're calculating the force, the work, when you're given a force at an angle to the displacement, we utilize this formula over here. More importantly, the one here on the right side. And this entire formula, what's written in the box, is what's shown on your AP formula physics sheet. The reason we have this cosine theta factor is because F cosine theta represents the parallel component of that force, the force that's making it move to the right. That's the part of the force that is actually doing the work. The units, as I mentioned earlier, which are in joules, which is the same thing as Newton meters. What kind of quantity is work? Well, you have been already told that energy is a scalar quantity. It doesn't have any direction. Work is equal to the change in energy, so work is also a scalar quantity. It only has a magnitude. So you would only say something like it has gained 2 joules of energy, the system, or it has lost, say, 1 joule of energy. But you would not say that it has 2 joules in the north direction. That would be incorrect because it's not a vector. However, if you look carefully, it involves the multiplication of 2 vectors, force, which has magnitude and direction, and displacement that has magnitude and direction. Technically speaking, this is the multiplication of 2 vectors yielding a scalar answer. Mathematically speaking, this particular multiplication of vectors is called a dot product. In general, let's say I have vector A, and I'm going to take the dot product of vector A and also vector B. The answer of that would be the magnitude of vector A, which we put absolute value signs around A, the magnitude of vector B, we put absolute value signs around vector B, and then cosine of theta. This is simply written usually A, which just represents the size of A, B, which is the magnitude of B, and then times the cosine of the angle between the 2 vectors. So this is the general mathematical definition for what is called a dot product of 2 vectors. This is not part of AP Physics 1. I'll leave the details of that particular vector product, scalar product, to the AP Physics C course. So don't worry about this particular definition. At this point, I think you're ready to practice utilizing this formula. So I would turn your attention to example 1, where work is done by pushing a crate, and example 2, where work is done in pulling a suitcase. In this particular case, we have a force being applied at an angle to the displacement. After practicing with these problems, I would also suggest that you go through the fill in the blank section in here to test your concept skills, to see if you can understand what work depends on, when is work positive or negative or zero, what angles would produce positive work, what angles would produce negative work, and so forth. Also, when is work zero? Well, if you push on a wall and the wall doesn't move, is there any work being done on the wall? No. What about if you're sliding down a slide and there's a normal force that is perpendicular to the displacement, which is shown as delta R? Is there any work done in that case? Remember, W is equal to F times D times cosine theta. And theta is the angle between the force and the displacement. In this particular case, it is 90 degrees. So you would get force times distance times the cosine of 90 degrees, but the cosine of 90 degrees is 0. So hence the work done by the normal force in this particular case is also 0. So whenever the force is perpendicular to the displacement, there's no work being done by that particular force. Then I want to look at scenarios where the work is positive, where energy is entering the system, such as case C. Also, take a look at conceptual example number 2, and you'll see some situations where the work might be 0, or you'll see situations where the work is positive or negative, depending on your starting and ending positions. And lastly, it's also important to be careful with the definition of work and how you use the terminology. Sometimes we talk about the work done by a specific object, or we talk about the work being done on a specific object. There is a difference between those two statements. If you go back to the Buffy and Biff example, in this particular case, Buffy, which is on the outside surroundings, is applying a force on the balloon. So we could say positive work is being done on the balloon. And since the balloon is part of our system, then we could say really work is done on the system, and hence energy is entering the system. There are situations where work is done by, say, the system on the surroundings. And in that particular case, energy would be leaving the system. And lastly, there might be several different objects that are doing work. For example, when you look at example number 1, here they're just looking for the work that was done by Sarah on the crate. But there are other forces acting on the crate. If you consider all the forces in this scenario, well, you could ask, what is the work done by the normal force? But the normal force is perpendicular to the displacement. Hopefully you realize it actually doesn't do any work because the angle is 90 degrees. And the same would lie true with the force of gravity because it's also perpendicular to the displacement. The force of friction would actually do negative work because when you look at that case, the work done by the frictional force would be the force of friction multiplied by the distance multiplied by the angle between the frictional force, which is backwards, and the displacement, which is going forwards. And so that angle is actually 180 degrees. And the cosine of 180 degrees is actually negative work. So it gives you a negative answer. And so really, friction is dissipating energy out of the box system. All of these terms can be quite confusing, and I'll try to take special attention to go over these details in class. The most important thing is that you understand the general idea that work is equal to the change in energy of the system, and the importance of defining your system and your surroundings appropriately, and understanding that work is also calculated by doing force times distance times the cosine of the angle between the force and the displacement.